Hi, everyone, and welcome to week 4 of Introduction to Logic. This week, we are going to talk about the natural deduction method for propositional logic, what is sometimes known as the proof method. And we're going to cover the first 4 rules of implication, which your textbook calls Rules of Implication 1. Before we dive in, I want to talk about what the proof method actually is. If you remember back to last week, we were talking about truth tables, and truth tables are what's known as a decision method. For any given argument in propositional logic, you can construct a truth table for it and determine whether that argument is valid or invalid with complete 100% reliability. There's no argument that you can't determine one way or the other whether the argument is valid or invalid. So right off the bat, I want to let you know that proofs are not a decision method. If you're able to complete a proof for an argument, that's sufficient to show that the argument is valid. But if you're not able to complete a proof, maybe you just can't see what step there is to do next. Maybe you're not sure how to use one of the rules. That doesn't mean that the argument is invalid. So again, proofs are not a decision method, but they're much more natural. In fact, they mirror how we use reasoning in ordinary language. That's why natural deduction is called natural deduction. It's supposed to mirror the way we use ordinary reasoning in our ordinary language and in our ordinary argumentation. Proofs basically look like this. You start with a premise, one or more premises, and then you have a conclusion that you're trying to demonstrate follows from those premises. So what I've done here is I've enumerated, this argument would have 2 premises and a conclusion. What you're trying to do in a series of steps is to demonstrate that the conclusion follows from those premises, as indicated by the arrow here, from a series of steps using valid inference rules and valid rules that dictate what types of statements follow from statements that are given to you in the argument. So all proofs look like this. You start out with a couple of premises that are, the premises of the argument. You're given some conclusion you're supposed to demonstrate, and then you deduce further things that have to be true given those premises, given these logical deduction rules that you're going to learn. And there are a bunch of these. We're going to learn 4 of them today. We're going to learn a fairly large number of these over the next several weeks. All of these, I should mention, are inside the inside cover of your textbook. So, and feel free to use that when doing your homework. You should. It would be almost impossible to do proofs without something like that handy. There's more I could say here, but I think I just want to dive in and start introducing these deduction rules. These deduction rules are fairly intuitive. In fact, like I said, the whole point of natural deduction is that they mirror the way we use reasoning in ordinary language. You'll have to kind of forgive these Latin names for these rules. These are the canonical names for these rules. And unfortunately, a couple of them are fairly easy to confuse with each other, like these 2 here, Modus Ponens and Modus Tollens, fairly easy to confuse those with each other. Let's go ahead and dive in. If you're given an argument like this, where you have if P implies Q right here, that says that if P is the case, then Q is the case. That's what an if-then statement means. If you then know that P is actually true, the antecedent of that conditional, you can deduce that Q follows from that. And this is probably the easiest inference rule to understand, right? If you have a statement like if P, then Q, and you know P is true, you know from that Q has to be true. So that one's pretty straightforward. I should say as well that P and Q here are just placeholders for any statement, either a simple statement or a complex statement. So for modus ponens, you could have something like if A, then B, A, therefore B. But you could also have something like this, if A and B, then C and D. That's a conditional as well. So here, A and B would stand for P, and C and D would stand for Q. If you then know that A and B are actually true on a separate line of the proof, you can conclude from that C and D are true as well. So again, this argument has that same pattern. If P, then Q, this is P, therefore Q. So any argument that has that pattern, no matter what you plug in for P and Q, whether a simple statement or a compound statement, Q would follow from those premises. Again, whether P or Q are simple or compound. Let's talk about modus tollens. Modus tollens also has a conditional statement, if P then Q, but in this case you have the negation of the consequent, not Q. And if you know that Q is false, then that means P has to be false as well. And I think this is a little harder to understand, but not much harder to understand. If P were true, Q would have to be true. That's what the first premise tells us. But if we know if Q is false, we know from that P has to be false. So again, the way Modus Tollens works is that you always have a conditional and you have a negation of the consequent, and you can conclude from that the negation of the antecedent. If you think about what those premises are really saying, you should be able to tell why that argument is valid. The next inference form is hypothetical syllogism. Oh, I should say as well that it's common in a proof to abbreviate these inference rules by their initials. Modus Ponens would be MP, Modus Tollens would be MT, and so on. The next rule I want to look at is called hypothetical syllogism. Your textbook calls it pure hypothetical syllogism. A hypothetical syllogism always looks like this. You have a conditional, if P then Q, and the consequent of that conditional, Q, is the antecedent of another conditional. In this case, Q implies R. And I think it's pretty easy to tell what follows from this. If you have P implies Q, but Q in turn implies R, that means that P would have to imply R. If P then Q, but if Q then R, so if P then R. Hence the conclusion there, if P then R. And the last rule we're going to look at today is called disjunctive syllogism. And if you remember, a disjunct is an either-or statement, as symbolized by the wedge in that first premise. So the first premise is not an if-then statement, it's a disjunction, an either-or statement, either P or Q. And if either P or Q is true, and you know one of them is false, in this case P, you know that Q has to be true. And this is exactly how we use an either-or statement. If either P or Q has to be true, but we know P is false, Q would have to be true. It is important to notice that for a disjunctive syllogism, you technically have to have the negation only of the term on the left. Now, obviously, P or Q and Q or P mean the same exact thing, but you're going to learn another rule in a couple of weeks that lets you switch around the order of a disjunction. You don't have that rule yet. So basically, a disjunctive syllogism always has to have the negation of the term on the left, in this case, the negation of P. So that's a disjunctive syllogism. These are probably the 4 easiest rules of everything you're going to learn when doing a proof. And again, don't let proofs become too overwhelming. They are really intuitive. In fact, they're way more fun, honestly, than doing truth tables. Truth tables can get unwieldy really quickly. I think you can see that as arguments get larger with more and more simple terms in them, truth tables are going to get massively unwieldy. An argument with only a single letter would only have 2 rows, but if an argument has 2 letters, it'll have 4 rows. If 3 letters, it'll be 8 rows, and you can see that that's exponential. So before you know it, you're doing truth tables that have 16 rows or 32 rows or 64 rows or 128 rows or even 512 rows or 1,024 rows. That is so massive you can't even fit it on the side of a building. You know, pretty soon we won't be able to fit it on the side of a skyscraper. So it's not a very extensible method for showing that arguments are valid or invalid. Proofs are a much more elegant way of showing that arguments are valid. All of the challenge in doing a proof is in pattern recognition. You have to be able to look at these, the statements that make up an argument and identify the patterns of those inference rules inside the statements of these arguments. And that just takes practice. So from here on out, for the rest of this video, I'm going to do example after example after example of proofs showing how to identify the patterns of those argument forms that we looked at just a moment ago. And just sort of teach you by example how to do proofs. And I think you'll see this is a lot more elegant than doing a truth table. In fact, if we did a truth table for this argument, there are 3 simple statements here. This truth table for this argument would have 8 rows, and we're going to be able to do a proof for this argument very, very quickly. So this argument, we're given 3 premises. Premise number 1 is F or D implies T. The main operator there would be a wedge. Make sure you notice that. The second premise is just not F, so we know F is false. And the third premise, D, tells us that D is true. And we're trying to prove the conclusion. So the first thing you want to do when you're doing a proof is make sure you look at the conclusion, because that's how we're going to know when we're done. We're going to start deducing further statements that have to be true given the truth of these premises. And as soon as we can get T on its own line of the proof, we're done, and we've shown that T necessarily follows from those premises. I'm just going to dive in. So we're going to add a new line, number 4. And there's only one starting place here, given the rules that we have. Premise number 1 tells us that either F is true or everything in those parentheses is true. But the second premise tells us that F is false, and that should flag you as a disjunctive syllogism. All right, this is a disjunct, either F or something else, but we know F is false. That's a disjunctive syllogism. It looks like this: P or Q, not P, therefore Q. And here Q would be D implies T. It's a complex statement. But you can see this matches the pattern for disjunctive syllogism, DS. So on line number 4, we know that if we have the negation of that first disjunct, the second disjunct has to be true. And the second disjunct in this case is this statement in parentheses, D implies T. Now, when you're doing a proof, you have to cite what premises you concluded that new line from and the rule that you used to deduce it. So in this case, this new statement, D implies T, excuse me, came from line 1 and line 2 using the rule disjunctive syllogism, DS. And again, just to make it really clear, premise number 1 tells us either F is the case or D implies T. Line number 2 tells us F is false, so we know that D implies T has to be true. That's what disjunctive syllogism does. All right, let's keep going here. Well, our new line number 4, says if D, then T, or D implies T. And line number 3 tells us that D is actually true. From those two statements, we can conclude that T has to be true. And why is that? Well, it comes from line 3 and line 4, according to the rule Modus Ponens, MP. And if you remember, Modus Ponens was P implies Q, P, therefore Q. And that's what we have going on here. We have if D, then T, D is true, therefore T has to be true. And we're done. Once we've reached the conclusion on its own line, we've shown that the argument has to be valid, that the conclusion T necessarily follows from the premises that are given. Okay, let's go on and do another example. In this argument on the screen, we've got 4 premises that are given to us. P implies that G implies T. And again, the main operator here is this horseshoe. Line number 2 tells us Q implies that T implies E. If Q, then T implies E. And lines 3 and 4 tell us that P is true and Q is true. And the conclusion here is that G implies E. So as soon as we get G implies E on its own line, we'll have shown that this argument is valid. Let's go ahead and dive in. We're going to add a new line number 5. And there are a couple of starting places here. Line 1 tells us that if P is true, something follows from that. And line 2 tells us that if Q is true, something follows from that. And lines 3 and 4 tell us P and Q are actually true. So we could start with either one of those two conditionals. Let's just start with the first one. If P is true, then we know that G implies T. That's because line 1 tells us if P is true, then we get that conditional inside parentheses. Line 3 tells us that P is actually true. And that follows from line 1 and line number 3 by Modus Ponens. And again, just to be really clear here, Modus Ponens is if P, then Q, P, therefore Q. Okay, let's keep going. Line 2 now tells us, I should say this is what's a little tricky about doing proofs. There's nothing in the proof that tells you what exactly to do next. You have to start looking for patterns, applying the rules that you notice, hoping that it's going to lead to that conclusion. That's why proofs are not a decision method. You know, if you don't see what to do next, that doesn't mean that the argument's invalid. It just means you didn't see what to do next. So this is not a mechanical plug and chug means of demonstrating that any given argument is valid. It takes a little bit of intuition and a little bit of human pattern recognition to demonstrate that any given argument is valid, to see what rule to apply next. So what I notice next is that line 2 right here tells us that if Q is true, this expression in parentheses has to be true. T implies E. But line 4 down here tells us that Q is actually true. From those two things, we can conclude that T implies E. And that follows from line number 2 and line number 4 by the same rule, Modus Ponens. If P, then Q, P, therefore Q. We're not done yet. We don't have G implies E on its own line. So let's add a new line and see what we can find. Well, line number 5 tells us that if G is true, we can get T from that. But 6 tells us that if T is true, we can get E from that, right? If T, then E. That looks an awful lot like a hypothetical syllogism. G implies T, but T implies E. And you can conclude from that that G implies E. And if you remember, I'm going to write it way up here, that this is according to the rule hypothetical syllogism. If P implies Q, but Q in turn implies something else, let's call it R, then we can get P implies R from that. That's exactly what we have going on here. G implies T, that's our P and our Q. T implies E, that's our Q and our R. So G implies E. And this would follow from line 5 and line 6 by hypothetical syllogism, HS, this rule right here. So you can see this is a lot more elegant than doing a proof. And in fact, if you look at this argument, we have P, G, T, E, P, G, T, E, and Q. Five lines. That means we would have 2 to the 5th power, which is 32 rows of a truth table to show that this argument is valid. And we did it in only 3 additional lines, 7 lines. So you can see this is a vastly more elegant way of showing that arguments are valid. The downside is it does take a little bit of intuition and a little bit of pattern recognition to find these argument patterns in these compound statements that make up the argument. Okay, let's keep going. I want to do a lot of examples for you. The next argument I've got for us here is, it's got 3 premises. J implies that K implies L. So if J, then this expression in parentheses, K implies L. The second premise says either L or J. It's a disjunction. And line number 3 says not L. And the conclusion that we're trying to show follows from these premises is not K. So when we get not K on its own line, we will have shown that this argument is a valid argument. Let's dive in. We're going to add a new line, line 4. Right off the bat, I noticed that lines 2 and 3 look like a disjunctive syllogism. A disjunctive syllogism is either P or Q, not P, therefore Q, right? Over here on the left, we've got L or J and not L. Same exact pattern as what you see here in the argument form. So from that, we can conclude that J is true. And again, I just want to make sure this reasoning is really clear. This is super easy reasoning, right? Line number 2 tells us either L or J is true. Well, if one of them is false, not L, we know that J has to be true. That's what a disjunctive syllogism is. So this would follow, I'm going to change color here to make this easy to see. This would follow from lines 2 and 3 by disjunctive syllogism, DS. Okay. Once we have J, notice that line number 1 says if J is true, then something else has to be true, this expression inside parentheses. And line number 4 happily tells us that J is true. So on line 5, we can conclude this consequent of this conditional in line 1, if K, then L. And again, just to make it really clear, line number 1 says if J is the case, then all of this in parentheses is the case. 4 says J is actually true, so we know from that that K implies L. And that's going to follow now from line, let me change color again here. That's going to follow from line 1 and line 4 by Modus Ponens, the rule that we looked at a couple of arguments ago. At a certain point, you'll have to commit these argument forms to memory. It just takes practice and practice and practice. So while you're doing the proofs that make up the exercises for your homework, just have the book open and have that list of rules right in front of you so you can see the argument patterns. I don't expect you to have all of these memorized right off the bat. Have them there with you. It'll take practice and practice and practice, though, for you to be able to habitually and instinctively notice the patterns that make up these argument forms inside the argument you're given. That's why you have to do so many arguments for homework, for practice. Again, logic is very practice-based. Unless you kind of train your mind to recognize these patterns, it's going to be very difficult to plug and chug through all these proofs. Okay, let's keep going. We're going to add a new line, line 6, and let's see what we can conclude. Well, in line 5, we have a new conditional, K implies L. But line 3, way up here, tells us that L is false. And that looks like the argument form for Modus Tollens, and that is P implies Q. If Q is false, that means P has to be false. And that's what we have going on here. We have K implies L right here. We know that L is false right here in line 3. From that, we can conclude that K is false, not K. And that follows from line 3 and line 5 by Modus Tollens, MT. And again, once you get that conclusion on its own line, you're done with the proof. We've got not K on its own line. Every new line that we added is a valid argument step, valid inference step. So that conclusion has to follow from those premises. Again, second you get that conclusion on its own line, you're done. Pretty straightforward. Let's do a slightly more complex proof. So in this proof, you're given 4 premises. If A, then E implies not F. Kind of a lengthy first premise. Line number 2 says either H, it's a disjunction, either H or not F implies M. 3 just says A is true, and 4 says H is false, not H. So we're going to start out by adding a new line, 5, and we'll see what we can deduce from this. I think the easiest thing to recognize here is that line 1 is a conditional, and in line 3, you've got the antecedent of that conditional, A. So again, just to make this really clear, line 1 says, if A is true, then this entire expression in parentheses has to be true. And line 3 tells us A is actually true. That means the consequent of that conditional inside parentheses has to be true. So we're on its own line now, we're going to get E implies not F from line 1 and line 3 by Modus Ponens. Okay. And again, just to be really clear, Modus Ponens, if P implies Q, P, therefore Q. Okay. Add a new line, line 6. The next thing I notice is that line number 2 is a disjunction. It says either H is true or this expression in parentheses has to be true. But line number 4 right here tells us H is false. That means that this expression in parentheses has to be true. And that, to me, looks like the form for disjunctive syllogism. P or Q, not P, therefore Q. So on line 6, we're going to get this expression inside parentheses. Not F implies M. According to what rule now? Let's see, it's going to come from line 2 and line 4 by this rule right here, disjunctive syllogism, DS. Okay. Let's see what else we've got. Okay. What I notice next is that in line 5 and line 6, you've got 2 conditionals where the same term, not F, is the antecedent of one and the consequent of the other. And if you kind of just naturally speak through the reasoning here, you should be able to see what follows from this. Line 5 says E implies not F. Line 6 says that not F in turn implies M. From that, you can conclude that E implies M. Again, just talk through the reasoning. If E, then not F. Line 6 says, but if not F is the case, then M has to be true. So you know that if E is true, you have to get M. If E, then M. And that's going to follow from line 5 and line 6 by hypothetical syllogism, HS. And just as a reminder, hypothetical syllogism is this. If P, then Q. If Q, then R. Therefore, if P, then R. HS, hypothetical syllogism. Okay, from this point on, I'm not going to keep drawing out each of these rules. You should be able to follow along with the rules inside your textbook, and we should be able to speed through the rest of these arguments. If you're having trouble committing these arguments to memory, talk through the reasoning behind them. You know, pronounce them like I'm doing here. If P, then Q, but P is true, therefore Q is true. That's Modus Ponens right here. For disjunctive syllogism, the first premise says either P is true or Q is true, but the second premise says P is false. You know from that Q has to be true. That's what disjunctive syllogism is. So if you try to just brute force memorize these without really paying attention to what they mean, you're really setting yourself up for a challenge. But if you talk through the reasoning, I hope you can make these rules intuitive and you can see the reasoning behind them, see why they're valid and why they work. Okay, let's do a couple more examples. Okay, in this argument, we have 3 premises. Line 1 says, if N is the case, then J implies P. Line 2 says, if J implies P, in other words, if all this in parentheses, then N implies J, all of that in parentheses. And line 3 says, N is true, just N on its own line. And we're trying to show that P is true. So the second we get P on its own line, using a series of valid deduction rules, valid deduction steps will have shown that this argument is valid. So we're going to add a new line, line 4, and see what we can deduce. Right off the bat, I notice that line 3 is the antecedent of the conditional in line 1. Line 1 says if n is true, then j implies p, and we know that n is true from line 3. So from there, we can conclude that j implies p, and that's going to follow from line 1 and line 3 by Modus Ponens. Okay. Notice now this is where things start to get a little tricky. And I'm just going to write it out here. So I'm going to refresh your memory on Modus Ponens. If P, then Q, P, therefore Q. This is Modus Ponens. Hopefully it's already reviewed and you've already got that one down pat. It's the easiest one of the bunch. But here, in line 2 and 4, we have an argument that matches that pattern. All of this, J implies P, would be P in this argument form right here. And all of this in parentheses right here would be Q in this argument form right here. And line 4 is the antecedent of that conditional. J implies P. Again, I'm just going to put it in a little subscript here. This is P right here in the argument form. So that says that we know that the consequent of this conditional in line 2 has to be true. And I think you can see this, and I'm just going to draw circles around it. Even though this is going to make the argument a little ugly, I want to draw explicit attention to it. Line 2 says, if all of this that I've circled here in yellow, that I'm circling right now, is true, then all of this has to be true. The second expression in parentheses, n implies j. Line 4 tells us that first expression is actually true. J implies p. So we know from that that n implies j, the second expression in parentheses. And that is the form for Modus Ponens. But here, P and Q don't stand for simple statements, just simple capital letters. They stand for complex expressions in parentheses. And you have to be able to recognize that in order to be able to do proofs effectively. Okay, so we have to, every time you get a new line, you have to cite the lines that it comes from and the rule that you use. So this came from line 2 and line 4 by Modus Ponens. If P, then Q, P, therefore Q. Okay. Well, there are a couple things we can do here. What I notice next is that in lines 4 and 5, we have two conditionals, and the antecedent of one conditional is the consequent of the other. In line 5, we have n implies j, but line 4 tells us that j implies p, and that is the form for a hypothetical syllogism. So from that, we can get n implies p, and that would follow from lines 4 and 5 by hypothetical syllogism, HS. Okay, we're almost done here. This new conditional that we got on line 6, n implies p, is a conditional. If n, then p. But way up here in line 3, we already knew that n was true. And from those two lines, it follows that p has to be true, right? If n, then p, and we know n is true, p has to be true. And that would follow from line 3 and line 6 by Modus Ponens. And once we get p on its own line, we're done. Right here. Okay. So we've shown that that argument is valid, and it only took 4 additional lines. So as you can see, proofs are a pretty elegant way of showing that arguments are valid. Okay, I've been marking these up a lot to demonstrate the patterns that I'm using to help you identify visually the patterns inside the argument. I'm going to try to be a little cleaner from here on out and produce fairly polished, finished proofs. And if you need a reminder on any of the rules, pause the video, go find the argument forms that I'm citing inside the textbook, look at the argument that I'm doing on the screen, and follow along and see if you can identify that pattern every step of the way. Okay, so this argument is looking a little scarier, but it's pretty straightforward still. We've got 4 premises. Line number 1 says either m is false or this expression in parentheses has to be true, b or not t. Line number 2 says B implies W. Line number 3 is not M. Now this is going to look a little strange if you haven't seen this, but you can have a negation of a negation. Of course, not M is just M. This is a double negation. Later in the course, there's going to be a rule that lets you cancel out double negations like this, but you don't have that rule yet. The way to think of this is that This is a negation of not M right here. So not M on its own is obviously the negation of M. Not M would be the negation of not M. So be really careful with these double negations when you see an example like that. You can't just eliminate them yet. You don't have that rule yet. There is a rule that's coming, but the textbook doesn't introduce that to you just yet. And line 4 says not W, and we're trying to show this conclusion, not T. Let's dive in. Add a new line, line 5. The first thing I notice is that line 3, not M, is the negation of this disjunct right here in the first premise. The first premise says either not M or this expression in parentheses, B or not T. 3 is not M. So we know that first disjunct, not M, is false. That's what not M means. So from that, we can conclude B or not T. And that would follow from line 1 and line 3 by disjunctive syllogism, DS. Okay, line 6. The next thing I notice is that in line 2, we have a conditional, if B then W, or B implies W. And line number 4 tells us that that consequent is W is false, not W. From those two statements, you can conclude that the antecedent has to be false, not B. And that would follow from line 2 and line 4 by Modus Tollens. Okay. We're very close to being done with this proof. Line 5 tells us that either B is true or not T is the case. Line 6 tells us that B is false. So we know from that that not T has to be the case, right? This disjunctive, that disjunction in line 5. And that would follow from line 5, excuse me, I'm trying to change colors here. Line 5 and line 6 by disjunctive syllogism, DS. And we're done. We've got not T on its own line. We've shown that that conclusion follows from those premises. Only 3 lines it took. It was a fairly scary looking set of premises there, but as you can see, it didn't take much to power through it and show that that conclusion follows. Okay. Okay, in this next argument, we've got 4 premises. The first premise says, if L is equivalent to N, that's what that biconditional is, then C. Line 2 says that either L is equivalent to N or P implies not E. Line 3 tells us that not E implies C, and line 4 tells us that C is false, or not C. And we're trying to show this conclusion, not P. Let's dive in. Especially now, this isn't always true when you're doing proofs, but right now you want to look at the simple premises. Like there's not going to be much there's not going to be anything you're able to do with the first 2 premises yet. You know that kind of scary expression, L is equivalent to N, is kind of locked inside those parentheses. But you can do something with premises 3 and 4 right off the bat. So line 3 says, if not E, then C, and line 4 tells us that C is false. So that's going to match the pattern for Modus Tollens. We have the negation of the consequent here in the conditional in line 3. That means we know that the negation of the antecedent has to be the case. So that's going to be not E. Here's our double negation. You've got to be really careful here. You can't just eliminate those right off the bat. You don't have a rule for that yet. So that's going to follow from line 3 and line 4 by Modus Tollens, MT. And again, if you're having trouble recognizing these patterns, go back and watch the first couple of arguments I did, or pause the video and open up your textbook and follow along with the examples that are given of the definitions of the deduction rules, so you can see what I'm doing here. And I think you can see, just to make it really clear, this is Modus Tollens is if P then Q. We have the negation of the consequent, not Q, and we get not P as a result. So here we've got our P and our Q, not Q, therefore not P. Okay. Line 6. Well, the next thing I notice is that in line 1, we've got another conditional. If all of that in parentheses right here, then C. But we know C is false. Line 4 told us that. So from that, we can get the negation of the antecedent of that conditional. The negation of L is equivalent to N. And that's going to follow from line 1 and line 4 by Modus Tollens. Okay. Well, line number 2 tells us that either L implies N or, either L is equivalent to N or P implies not E. But in line 6, we learned that expression in parentheses, L is equivalent to N, is actually false, right? We have the negation of L is equivalent to N in line 6. So from that, we know that this other expression in parentheses on the right side of that disjunction has to be true. So P implies not E. And that's going to follow from line 2 and line 6 by disjunctive syllogism. And again, just to make it really clear, line 2 says either L is equivalent to N, that's the expression in parentheses on the left, or P implies not E, that's the expression in parentheses on the right. Line 6 told us that that expression on the left, L is equivalent to N, is actually false. So we know that the expression in parentheses on the right has to be true. That's what we got on line 7, P implies not E. Let's add a new line, line 8. Okay. So our new expression on line 7, P implies not E, that's a conditional, if P then not E. But on line 5, we know that not E is false. We have not E, or the negation of not E. So from that, we can conclude the negation of this antecedent in line 7, and that will give us not P. And that will follow from line 5 and line 7 by Modus Tollens. And we're done. We've got not P on its own line, so we've shown that that argument is a valid argument. And it only took 4 steps. Okay. Let's do another one. This one's going to look a little scary, but don't be intimidated by it. The first premise says if B implies not M, right? If all of this in parentheses, then T implies not S. Line 2 says B implies K, or if B, then K. Line 3 says K implies not M. Line 4 says that if not S, then N. And we're trying to show this conclusion, T implies N. So let's dive in. So right off the bat, I notice that on lines 2 and 3, we've got 2 conditionals, and the antecedent of one is the consequent of the other. So we've got B implies K on line 2, but line 3 tells us that K implies not M. So from that, we know that B has to imply not M. Again, just to talk through the reasoning, line 2 says if B, then K, but line 3 says, but if K is true, then not M is true. So if B, then not M. And that's going to follow from lines 2 and 3 by hypothetical syllogism, HS. Okay. Now, notice that line 5 is the antecedent of this conditional on line 1. Line 1 said, if B implies not M, then we get that expression on the right in parentheses. And line 5, we know that B implies not M. So from that, we can get T implies not S, which is the expression in parentheses way up here in line 1. And that would follow now from line 1 and line 5 by Modus Ponens. Okay. Excuse me. So we're trying to get T implies N. That's the goal. That's the conclusion that we're trying to show follows from these premises. The next thing I notice is that we have 2 conditionals here where the antecedent of one is the consequent of the other. I'm going to just circle them here, line 4 and line 6. Line 6 says that if T is true, then not S has to be the case. But line 4 says that if not S is the case, we get N. From those 2 premises, you can conclude if T, then N. And that's going to follow from lines 4 and line 6 by hypothetical syllogism, HS. And we're done. Once you get the conclusion on its own line, you've shown that the argument is valid. And here it only took 3 additional lines. So even though we had a fairly scary looking first premise, notice that it didn't take much to power through this and show that that conclusion followed. This is the power of natural deduction for showing that arguments are valid. Okay, let's do a few more. Okay, this argument, we've got 4 premises. The first one says, if not A, then B implies not C. Line 2 says, if not D, then not C implies A. Line 3 tells us that either D or not A is true. And line 4 says not D. D is false, in other words. And the conclusion that we're trying to show is not B. So once we've shown not B on its own line, we're done. Let's add a new line, line 5. There are a couple of starting points here, and what's kind of empowering but also a little frustrating about doing proofs is that there's no rule that tells you what you have to do next, unlike in a truth table where it's very prescriptive and deterministic. Here we've got a couple of things we can do. You might notice that lines 3 and 4, right here and right here, match the form for disjunctive syllogism. So we could do a disjunctive syllogism right off the bat. But you might also notice that line 2 and line 4 match the form for modus ponens. So you could do a modus ponens step. We'll probably have to do both of those steps, so it doesn't really matter where you start. I like to start with the things that look easiest, honestly. Sometimes that can actually make the proof a little longer. Sometimes you can actually take a shorter path to getting the conclusion by starting with something that looks a little more counterintuitive. But I like proofs to be easy to understand. So I want to what I want to do is do the rule that is the simplest rule I can do. And that's, again, later in the course, that's actually not going to help you. You want to be a bit more strategic. But for now, let's just do the things that are really easy to do. So lines 3 and 4, we said match the form for disjunctive syllogism. Line 3 says that either D or not A, but line 4 told us that D is false. So from that, we know that not A has to be the case. And that would follow from lines 3 and 4 by disjunctive syllogism. And a moment ago, we said that lines 2 and 4 match the pattern for modus ponens. So let's do that step next and get that out of the way. Line 2 says, if not D, then all of that expression in parentheses, not C, implies A. Line 4 says not D is actually the case, so we get not C implies A, that expression up here in line 2, inside parentheses. And that follows now from line 2 and line 4 by modus ponens. Okay, line 7. Notice now that we have the antecedent of that conditional in line 1. Line 1 says, if not A, then B implies not C. 5 says that not A is actually the case, so we get B implies not C. That would follow from line 1 and line 4 by modus ponens. Okay. Now notice line 6 and 7. Again, you've got 2 conditionals and the consequent of one is the antecedent of the other. Line 7 says B implies not C, but line 6 tells us that not C in turn implies A. We know from that that B implies A. And that would follow from lines 6 and 7 by hypothetical syllogism, HS. Now, always keep the goal in mind. We're trying to show not B. So the second we get not B on its own line, using a valid inference rule, we're done. Okay, so line 8 says B implies A, but in line 5, we know that A is false, and that tells us that B has to be false according to Modus Tollens. So on line 9, we get not B, which is our conclusion. So this is going to be the last line. This is going to follow from line 5 and line 8 by Modus Tollens. And we are done. It only took 5 additional lines. Okay, let's move on. I think you can see these are a lot more fun and easier to do and take a lot less ink than doing a truth table. Okay, so we've got 4 premises, H implies this long expression inside the brackets, and it's helpful not even to worry about that. Notice that this is still a conditional. If H, then something in brackets that we don't have to worry about yet. Line 2 says not D implies E. Line 3 says either E or H. Line 4 tells us that E is false, and we're trying to show the conclusion, not C. Okay. There are a couple places we could start. Notice that in line 2, we have a conditional, not D implies E, and we know that, the consequent of that conditional, E, is false. That's what 4 tells us. In line 3, we also have E or H, and we know E is false. Line 4 tells us that. So we could do a Modus Tollens step with lines 2 and 4, or we could start with a disjunctive syllogism when lines 3 or 4. Let's start with lines 2 and 4. So line 2 tells us not D implies E. 4 tells us that the consequent of that conditional, E, is false. So we know that the antecedent has to be false. And here you've got to be really careful. The antecedent is not D. And for that to be false, that would be not D. 2 tildes back to back. And that's going to follow now from lines 2 and 4 by Modus Tollens, MT. Okay. Let's do that disjunctive syllogism step we mentioned. So on lines 3 and 4, line 3 is either E or H, it's a disjunction. Line 4 tells us that E is false, so we know H has to be true. And that's going to follow from lines 3 and 4 by disjunctive syllogism, DS. Okay. Line 7. Now here's where we're going to use that very scary looking first premise, which isn't as scary as it looks. Line 1 says, if H, then that entire expression in brackets follows. And we don't want to worry about what that expression is yet. We just know that if H is true, we get that expression in brackets. And line 6 tells us that H is true. So we know that that entire expression inside the brackets has to be true. All of this right here that I'm going to indicate with a yellow line. So in line 7, I'm going to get that entire bracketed expression. Not E implies, with parentheses here, don't miss anything, C implies not D. All of that. And that's going to follow now from line 1 and line 6 by Modus Ponens. So even though that's a fairly scary looking expression, it still has the form P implies Q, P therefore Q. It just so happens here that Q stands for this entire expression in the brackets. That's what we got on line 7, Q on its own line. Okay, line 8. The next thing I notice is that 7 is a conditional. If not E, then C implies not D. If not E, then that expression inside parentheses. And we have not E on line 4. And so by Modus Ponens, we can get that C implies not D. And that's going to follow now from line 4 and line 7 by Modus Ponens. So again, notice that there's nothing to tell me what I have to do next. You have to rely on your pattern recognition skills to be able to identify these argument patterns inside the statements that you're given. And that just takes practice. So please, please, please do plenty of practice. Even do extra, redo the ones I've done in the video, do the ones in your homework, do the sample exercises from section 7.1 of your textbook. Get as much practice as you can on this. As you can see, any given proof doesn't take very long. Your homework probably won't take you very long this week, but get lots of extra practice on this. Okay, the next thing I notice is that on line 8, we've got a conditional. C implies not D. But number 5 tells us that not D is false. We have not D. From that, we know that the antecedent of the conditional in line 8, C, has to be false, or not C. And that would follow now from line 5 and line 8 by Modus Tollens. And we're done. Once we've got not C on its own line, that's the conclusion we were trying to show followed. We've finished the proof and we've shown that argument is valid. Didn't take very many steps. Okay. As we keep going through the rest of the exercises I have for you guys, these are going to get a little sort of bigger, longer, scarier looking. But if you break them down, as I'm doing here, you can see that they're not terribly complicated. Okay, line 5. Well, let me run through the premises first, like I've done before. You know, at a certain point, you need to be able to identify these yourself. And I'm reading each premise out loud to you to reinforce what I notice when I see these statements. So line 1 is a conditional. It says, if this expression in parentheses, if C implies M, then this other expression in parentheses, N implies P. Line 2 says that if C implies N, be careful here with it, we have M's and N's. That's a little almost visually cluttery. So if C implies N, then this other expression in parentheses on the right, N implies M. On line 3, we've got a conditional. If C implies P, then, make sure you notice the main operator there, then, not M. Line 4 says that C implies N, and we're trying to show that from that C is false. Okay, let's dive in. The thing I notice right off the bat is that line 4 is the antecedent of this conditional in line 1, right? Or excuse me, in line 2. Line 2 says if C implies N, then we get this expression in parentheses on the right, N implies M. Line 4 says that C does imply N, so we know from that that N implies M. And that's going to follow now from line 2 and line 4 by Modus Ponens. And again, if you need to review the rules, pause the video, crack open the textbook, and look at what Modus Ponens does. Look at line 2 and line 4, and you should be able to see the pattern inside those statements. Okay, the next thing I notice is that in lines 4 and 5, you've got two conditionals, and again, the consequent of one is the antecedent of the other. Line 4 says, if C, then N. Line 5 says, but if N, then M. So we know from that C implies M. And that's going to follow from line 4 and line 5 by hypothetical syllogism, HS. But once we know that C implies M, that's the antecedent of this conditional in line 1. So from that, we know that N implies P, the consequent of that conditional in line 1. And that's going to follow from line 1 and line 6 by Modus Ponens. Okay, next line, line 8. Okay, the next thing I notice is that on line 4 and line 7, we've got two conditionals. Again, the consequent of one is the antecedent of the other. Line 4 says, if C, then N. Line 7 says, if N, then P. From that, it follows that if C, then P. And that would follow from line 4 and line 7 by hypothetical syllogism. Okay. But that gives us the antecedent of this conditional in line 3, if C, then P. If that is the case, you get not M. So on the next line, we can write not M. And that's going to follow now from line 3 and line 8 by Modus Ponens. Line 10. Remember, we're trying to get not C on its own. And in line 6, we've got a conditional. If C, then M. Line 9 tells us that M is false. We know from that C has to be false. And that's going to follow now from line 6 and line 9 by Modus Tollens, MT. And we're done. We've got not C on its own line. Okay, I've got one more for you guys, and then I will give you your time back, and you can get lots and lots of practice doing proofs on your homework exercises for the week. We have 4 premises. Line 1 says that if not A, then that entire bracketed expression on the right. Line 2 says if not R, then that entire bracketed expression on the right. Don't worry about what those are yet. Line 3 says that if T or D, then not R. Line 4 says T or D is actually the case, and we're trying to show that D follows from that. So let's dive in. Line 5. The very first thing I notice is that line 4, T or D, is the antecedent of the conditional here in line 3. So from that, we know not R has to be the case. And that's going to follow now from line 3 and line 4 by Modus Ponens. Okay, next line, line 6. Once we have not R, that's the antecedent of the conditional in line 2 right here. So we know that that bracketed expression, R or A implies R, inside brackets has to be true. R or, in parentheses now, A implies R. And that's going to follow from line 2 and line 5 by Modus Ponens. But that expression we got on line 6, R or A implies R, is a disjunction. It says either R is the case or that expression in parentheses, A implies R is the case. But line 5 tells us that R is false. From those two statements, we know that A has to imply R. That expression in parentheses has to be true. That's going to follow now from line 5 and line 6 by disjunctive syllogism. Okay. So line 7, our new line, says if A, then R. Line 5, we know that R is false. The consequent of that conditional is false. According to Modus Tollens, we know that the antecedent then has to be false, or not A. And that's going to follow now from line 5 and line 7 by Modus Tollens. Once we know A is false, that's the antecedent of the conditional way up here in line 1. If not A, then this entire bracketed expression on the right. So we know that A or T implies R has to be the case. And that's going to follow from line 1 and line 8 by Modus Ponens. But that's a disjunction. It says A or T implies R. And on line 8, we know that A is false. So we know that T implies R has to be the case, that expression in parentheses. That's going to follow now from line 8 and line 9 by disjunctive syllogism. Okay, I'm going to move way up here to the top right, start a new line, line 11. In fact, I'll draw a little dividing line here to keep this visually clear. Okay, the next thing I notice is that on line 10, we've got an if-then statement, if T, then R. And way up here in line 5, we have not R. That's going to match the pattern for Modus Tollens, so we know that the antecedent of that conditional in line 10 has to be false, or not T. And that's going to follow now from line, let's see, it's going to follow from line 5 and line 10, excuse me, by Modus Tollens. I think we're almost done, not quite. Excuse me. Once we have not T, we actually have the negation of one of the disjuncts way up here in line 4. Don't forget about the statements up above that are given to you. You're allowed to use any lines that occur previously in the proof, with some exceptions that we'll talk about here in a few weeks. But for now, you're able to cite any previous lines. We haven't used line 4 yet, and that should kind of stand out to you. Line 4 says either T or D. Line 11, the line we just got, says that T is false, so we know from those that D has to be true. And that's going to follow now from line, let's see, what was it? Line 4 and line 11 by disjunctive syllogism. And notice that we're done. We were trying to show that D has to be the case. We showed that on its own line here in line 12, and that shows that this argument is valid, and it only took 12 lines. Way faster than doing a truth table for this argument. This would have been a pretty large truth table for this argument. Something like probably, let's see, how many lines? A, T, R, and D would have been 16 lines to do a truth table. And we did this in 12 lines, including the 4 that were given. So this was quite a bit more elegant. That's the last example I have for you. I want, for your homework, do the odd numbered exercises from Roman numeral, let's see, it's section 7.1, Roman numeral number 3, and do all the odd exercises, all the complete proofs, in other words. But get lots of extra practice. Redo the exercises that I did here in the video. Do the practice exercises that are given inside the textbook chapter itself. Again, let me just refresh, kind of sum everything up here. In an argument, you're given some number of premises and a conclusion. Every line of a proof needs to follow by one of these valid inference rules. I'll scroll back up here and run through the rules one more time. Modus Ponens, MP, says that if P implies Q and you have P then Q follows from that. And again, P or Q here can stand for a simple statement, either, just a simple capital set of capital letters, or P or Q could stand for compound expressions in parentheses or brackets or braces. And all the entire challenge of doing proofs rests with your ability to recognize these argument patterns in compound statements. Modus Tollens, MT, says, if P implies Q, and if you have the negation of the consequent, not Q, you know that the negation of the antecedent, not P, has to be the case. Down here, hypothetical syllogism. Basically, there are two conditionals where the antecedent of one is the consequent of the other. In this case, P implies Q, but Q implies R, so you know that if P is true, then R has to be true. You get another conditional, P implies R. That's hypothetical syllogism, or HS. And the last argument form, disjunctive syllogism, says either P or Q, but P is false. You know from that that Q has to be true. Again, P or Q could stand for atomic statements, capital letters, or they could stand for compound expressions in brackets. So again, just to summarize proofs, you're given some number of premises and a conclusion. You obviously can't cite the conclusion because that's what you're trying to prove. Every line needs to follow by one of the inference rules. You always cite the line numbers that the new line comes from and the rule that you use to deduce that line. And if you can show that the conclusion of the argument follows on its own line, you will have shown that the argument is a valid argument. But if you're unable to show that that a conclusion follows from a set of premises, that doesn't automatically mean the argument is invalid, because there's just no way to know if you just weren't, frankly, clever enough to notice the next step of the proof to do. In fact, it's been shown that there are some arguments that there simply is no mechanical method for evaluating the argument. In other words, you can't write a computer program to crank out a proof for any given argument. Some proofs, kind of get you stuck in a feedback loop. Those are well beyond what we're looking at right now. But in other words, proofs are not a decision method. They're not a 100% reliable way of taking any given argument and showing that it's valid or invalid with certainty. That's what truth tables are for. But if you can generate a proof for an argument where each line of the proof follows by a valid inference rule, and you get the conclusion on its own line, and every step is a validly applied instance of an inference rule, you will have shown that the argument is a valid argument. But proofs are not a way of demonstrating invalidity. There's no way to use a proof to show that an argument is invalid. Okay, that's all I've got for you guys. You got plenty of exercises to do. Definitely contact me if you have any questions. If you want to walk through any examples together, we could jump on Zoom, or we could look at an example by email. Always happy to help, but definitely get lots of practice. It's like learning piano. You just can't learn it if you don't get practice doing it. So, definitely are going to do your exercises, but if you're not comfortable instantly recognizing modus ponens or disjunctive syllogism or modus tollens or hypothetical syllogism in these various examples that we've looked at, get more practice and make sure you pause the video, look at the examples, look at each line, make sure you can identify how it follows given the lines that I've cited here in the video. And happily, I think in a way, this is why learning logic by video is actually a little easier. You can pause the video, you can look at each line, see how it follows, and look at the textbook and look at the inference rule and see that it follows, and look at the next step, pause the video, do that if you need to. If you're following along, that's great. Okay, you guys have a great week, and I'll look to receive your homework exercises by the end of Sunday by 11:59 p.m. on Sunday. Have a great week.